let's do a trig sub. Let's suppose we have something like this. This setup is super common, so and just making up problems to do trig sub, sometimes you end up with integrals that are nasty and not integrable, so we'll just go as far, we'll get through the setup. That's the most important part, getting through the setup. So in general, with our trig sub, we want to have a sum or difference of squares with a 1. That just makes it easier in the long run to do the integration. So what are we going to do to get a difference or sum of squares with a 1?
We pull out a 9.
Factor out the 9. And what is, that 9 is in the denominator, so it's got to stay in the denominator. And what power should be on it? The 5/2. So that power in the denominator stays on the constant that you pull it out. So if that's a square root stays on it. If it's a square stays on it. Whatever the power is, that has to stay on it. Okay, so numerator is not changing yet. Still have the dx down here. When we factor out the 9, we're left with a 1. And the whole idea here is that we're going to want to write it as a difference of squares. So if you want to put a 9 and a 9 here to help you visualize what's happening, this 9 right there is the one that's factored out to the front. And then we're left with an x squared divided by 9 that we want to write as a square, so that's x divided by 3 quantity squared. So that is our basic setup. And then we have to decide sine, secant, or tangent for the substitution. What do you think, sine, secant, or tangent? Sine? So 1 minus u squared is sine. U squared minus 1 is secant. So we're going to let x divided by 3 be sine.
Where did that square root come from?
Oh, that's a 5/2. Thank you. I have no idea. It's Monday. Yeah, 5/2. Hopefully some other people were looking at that saying the same thing. Okay, so that's a 5/2 power in the denominator. Now let's put the dx up there. Okay, so x over 3 is sine. Then we take the derivative of both sides of that substitution step. Derivative on the left is 1/3 multiplied by dx cosine of theta d theta. When we look at that 9 to the 5/2, we should see that as the square root of 9 to the 5th. The square root of 9 is 3. So let's just do it one step at a time. We'll have 3 to the 5th. X squared, if we look right here, x is going to be 3 sine theta. If we square it, we're going to get 9 sine squared. And then if we look at the dx, dx is going to be 3 cosine of theta d theta. All right, any questions there?
Wait, why is it the 9 sine squared first? Like, what'd you do to get that?
So this is an x to the 2. So if we look over here, x is equal to 3 sine of theta, so we square 3 sine theta. So 3 sine theta.
Oh, I see. You just moved it over and then squared it.
Right.
I see.
Yeah, we move the 3 over and then square it. Same with the differential. dx is 3 cosine theta. So we have to replace this dx right there
Oh,
with what it's equal to, and if we move the 3 over there, it's 3 cosine theta. Okay, denominator. We ready to go to the denominator?
We're just gonna process this. Okay.
All right, go into the denominator. So that's going to be 1 minus sine squared. All raised to the 5/2 power. Because x over 3 is sine, so 1 minus sine squared. We're in the denominator. Everyone okay with that? 1 minus sine squared gets replaced with cosine squared. And notice in the numerator here we have 3 3's. 9 is 3 times 3. We have 3 3's. Down here we have 3 to the 5th, so we're going to be left with 2 3's, which is 9. Whoops. Power. What should the power in cosine be?
Squared.
Squared. And then that's all raised to the 5/2. So this is going to give us 1/9. Numerator, let's just leave that alone for the moment. And down here we have cosine to the what power? 5th power? 5th power? And then canceling out 1 cosine gives cosine to the 4th in the denominator. Okay. Not an odd power on that sign, so we can't use one of those 8-3 tricks, odd power on sine or cosine. What we want to do here is convert the numerator so that we only have 1 trig function in this integrand. So we can convert that numerator using Pythagorean theorem. Whenever we have even powers, we need to do some manipulation. A lot of times it's power reduction. But power reduction here is not going to help us because then we'll have, in the numerator, we'd have a 2 theta and denominator 1 theta. You always want the angles to match. Bless you. And now what do you think we're going to do? Split the fraction. So split the fraction, we're going to have 1/9. 1 divided by cosine to the 4th is secant to the 4th. And then over there, what do we end up with? Secant squared? One of these has an antiderivative. What's the antiderivative for secant squared? Tangent. This one we have to do some work on. So we have an even power. If you have an even power on secant, you pull 2 off and convert the leftovers. So let's keep on trucking. So we're going to have 1/9 integral. We're going to pull off. We'll do it in 2 steps. The theta. And then let's distribute the 1/9 to the other integral, which we said has an antiderivative of tangent. So that's where we're at so far. Integral of secant squared is tangent. Okay, so the rule for an even power of secant, we pulled off to, we're converting the leftovers now. How do we convert these leftovers?
You saw.
We convert them with,
I had a question.
yeah,
Where did that negative 1 over 9 come from?
this negative, this 1/9 gets distributed here and here. So 1/9 secant to the 4th minus 1/9 secant squared. So it comes from that.
Okay, couldn't you just keep that out there and then slug
You
it?
could, yeah, you could have some big monster brackets.
Which one would be better? To just
Doesn't matter.
Okay.
Yeah, whatever makes sense. You
Why
could
does
put-
it stay in front of that, so on the right side where it says leftovers, why does it stay outside of the integral and also go in front of negative, or the tan theta?
So we could put this on the constants can be either on the inside or the outside of an integral symbol. So we could put it on the inside if we wanted.
Well, so like, why is it next to the tan on the inside though?
This is no longer like that's out,
Oh.
right? That's the end of this,
Oh, right, I didn't see the detail.
right? So the minus 1/9 is beyond the integral.
Yeah, because you split the
Integral got split.
No.
The integral got distributed. Yeah. Okie dokie. So, and I think I heard someone say 1 plus tangent squared somewhere. Maybe. Maybe? And then what are we going to let u be for that left integral? Something happened.
squared?
Yeah, that should be secant squared. All of a sudden I was like, wait a minute, the derivative of tangent's not working. So all we did was convert these leftovers to 1 plus tan squared. Now we let u be tangent. So come over here, we'll let u be tangent. U sub du is secant squared. So the front integral becomes the integral of 1 plus u squared du. Right? Everything disappears there. And then minus 1/9 tan theta plus c. This we can integrate directly. Integral of 1 is u, and then plus u cubed over 3. And there is a plus c, but we're just going to think of it as merging with this constant over here. We don't need a second plus c. We already have a constant of integration, so we can just leave it. We're almost there. Right around the corner. So back substitute the tangent in, we get 1/9 tangent plus 1/27 tangent cubed minus, oh, look at that. Cancellation? So 1/9 tangent minus 1/9 tangent, so we have cancellation. Those two go away. And there's our answer in theta, but what do we have to do? What's our very last step? Cool triangle. We need our cool triangle.
No.
From right there, x over 3 is sine theta. So here is how we build our cool triangle. Always like it's in quadrant 1. Sine is opposite over hypotenuse. Opposite hypotenuse. And then what is that missing side? 3 squared minus x squared, so 9 minus x squared. And that 9 minus x squared should match something up here, and it does, 9 minus x squared. Tangent is opposite over adjacent. It's the only thing left to do. Come in over here. We have 1/27th opposite over adjacent. So we're going to have x divided by square root of 9 minus x squared. All of that is cubed plus c. Final form, x cubed over 9 minus x halves, x squared to the 3 halves. Let's see. Questions? If you can't articulate a question, you can just point and grunt. If you can't come up with a question. Oh, that feels so good. All right, any step there?
So in the homework problems, I'm pretty sure there was like a one like tangent to the fourth, and I didn't know where to go for there.
Mhm.
Would that work for that too?
Tangent to the 4, so you have tangent to an even power. Yeah, you're going to do that kind of thing. You're going to take, what you're going to do is do tan squared, and then do sec squared minus 1 times sec squared minus 1.
Okay.
Yeah, that's going to be some work. Yeah, if we don't have the two conditions, either secant to an even or tangent to an odd, we have to go back to the Pythagorean theorem and then do stuff. You could also convert to sines and cosines there, but you'll have the same problem. You have to do Pythagorean conversion. Okay, everyone okay with this? You could redo this one now? All right, pop quiz. Pop quiz. All right, let's do a completing the square one. Whenever we have a quadratic that's not factorable, we complete the square. So we've seen this a bunch. If we have a quadratic that's not factorable, we complete the square. If we do have a quadratic that's factorable, we'll use another technique, which we're going to learn in a little while. Another technique. So, but this is not factorable. So we want to complete the square. What is the number that we need to complete the square? Divide that by 2 and square. So we need 9. So we can just borrow that 9 from the 34, giving us that. Rewrite the 34 as 9 plus 25. This is now a perfect square trinomial, obviously. Right? It's a perfect square trinomial if that constant at the end is the square of half the middle term. If that's the square of half the middle term, it's a perfect square trinomial. That can factor then into x plus x minus 3, quantity squared, plus 25. We almost have it in inverse trig form. What are we going to factor out? 25. We want it to be a 1 over there. Sum of squares with a 1. So factoring the 25 in the denominator, there's no power. So it's just coming out as a 25. There's no power. There is not a 25 over here, though, so we need to introduce the 25 in the denominator. So we've got that. Yeah. So we have two choices here. What do you guys want to do? How should we integrate this? Want to do trig sub?
Yeah.
Trig sub?
So what was the other?
I'll tell you the other option in one moment.
Let's do the tricks up.
I'll tell you the other option in one moment.
You?
Sine, secant, or tangent?
Yeah.
What's the derivative of the left side? The left
Oh.
side. 1/5. 1/5 is the derivative of the left side. Derivative of the right side. All right, so let's do our substitution. Back in, so we're going to have a 1/25. In the numerator, we have a dx. dx is 5 secant squared. How about the denominator? Tan squared plus 1, which is secant squared. Tan squared plus 1 is secant squared.
Is it really?
Tan squared plus 1? Yeah, secant squared. So this all reduces to 1/5 integral of d theta. Secant squared's canceled. 5 pops to the front. Integral of d theta. Theta plus c. And then what is theta? Theta is inverse tan. And that is our answer. If you get to this stage where everything cancels and you just have a d theta, you missed something. Something went right by. What was it? The thing that went right by is that it's in inverse tangent form already. You don't need trig sub. You don't need it. Right here, this is in inverse tangent form. The antiderivative here is the inverse tangent of whatever's in the parentheses. And then what do we put here for RCR? So we come up here, we take the derivative of this, which is 1/5. So we divide by 1/5, which means multiply by 5. So that's the RCR part right there. RCR means take the derivative of this.
So why do you divide by 1/5 rather than multiply?
Because we're doing reverse chain rule, not chain rule. When you're differentiating, you multiply by the derivative of whatever it is. When you're integrating, you divide by it. So integration, division, chain rule, multiplication. And we get the same answer, of course.
Are both valid for like the test?
Mhm. Yeah, so if you forget, so the nice thing is that if you don't recognize that it's already in the inverse tangent form, you're going to get the same answer anyway. It doesn't really matter.
So like, when can you tell that it is an inverse tangent?
If you end up, well, so the form of inverse tangent is if we have, let's use u's, if we have something like this, that integrates the inverse tangent of u. So if we have something of that form, and that's what we have here, we have 1 plus u squared.
So then is it applicable to like every tangent?
Yeah.
Like trigonometric substitution problem, I guess?
Yes. So for example, if we had something like this, let's suppose we have the integral of dx over the square root of 9 minus x squared. So if we have that one, first we're going to factor out the 9. So we're going to end up with 1/3 integral dx divided by square root of 1 minus, hopefully you're seeing this by now, that. This is in inverse sine form. We should be able to write the antiderivative right now. All right, this is inverse sine. So this is going to be equal to 1/3, leave some space for the reverse chain rule, inverse sine of x divided by 3. And what's going to go in the reverse chain rule place? 3. The derivative of x over 3 is 1/3. Dividing by 1/3 is multiplying by 5.
What?
What? Dividing by 1/3 is multiplying by 3?
It's only 3:30.
I know. Get ready. So we have that. Dividing by 3, dividing by 1/3 is multiplying by 5. Oh boy. What was in that lollipop?
Is this your room? Can you make that up?
So now, if we didn't recognize that it was in the inverse sine form, what would you have done? You would have said, what would you have let x over 3 be? Sine of theta. And when you differentiate here, you'd have 1/3 dx equals cosine theta d theta. So let's go through it here. So we're going to come down. So this will be 1/3 integral. Dx is 3 cosine theta d theta. And what's the denominator? 1 minus sine squared, which is cosine squared. Square root of cosine squared? Cosine. And it all cancels.
Wow.
So those cancel, and we end up with the integral of d theta, which is theta. And theta is the inverse sine of x over 3. So if you forget your basic forms, it's not that big a deal. As long as you know your trig sub, you don't even have to remember your basic forms anymore. All you need to know is sine, secant, or tangent.
So I see when the 1 is leading, it's like we choose, I know like that we choose
Sine.
sine.
Yep.
But which one is it when it's like in the end?
If it's trailing, it's going to be secant.
And it's also minus, right?
Yes. So secant is a difference of squares with a trailing one, when the one is second.
Minus 1, right?
Second?
Minus 1?
Minus 1, yeah. Secant. Second secant. Second secant. Yeah, all right. Amazing. So let's do this one here. Polynomial in the denominator that's not factorable, so we have to complete the square, but you can't complete the square until the coefficient of u squared is 1. So we're going to factor out the 2. Right? Whenever you complete the square, the coefficient of the square term must be 1. You can't do like divide by 2 and square for a random quadratic. The leading coefficient has to be 1. Before you can complete the square, this must be a 1. Or you can't complete the square. So factor out the 2, make that leading coefficient 1, and then we'll complete the square. Or you'll complete the square. You guys do this one. I'm sick of doing that.
That's 9, right?
I'm dividing by 1/3 and getting 5.
I trust you, Mr. Ross. And you complete that.
All right, so you guys complete the square and do your trig sub.
You can't
Okay. Question for you.
Yeah.
Is this
Lost me
this
at
like
Summary?
yeah?
complete the square.
Yes.
Okay.
That is 100%. Yep. That is correct.
Plus 9. Yeah. No, she just went factor out 1/9.
Come on. I never said it. Never said it. Do as I say. No, don't do as I say.
Don't do as you say.
Do as
So, what do we do?
What do you do?
3 squared plus 1.
Just got my arrows and a low. Fine. Yeah, I think I shall not worry about that guy.
3. How wrong?
Do you have any hand sanitizer? Let's see. U complete square.
U minus 3 squared.
Sure.
I forgot to say I actually pulled it out. It's down there.
That's what
I don't know if it's right.
There.
So, yeah, now that's factorable.
U minus 3.
So,
Actually, say it.
and where's the square?
I forgot to say
This is what I have so far.
Is it inverse pan?
I believe so. If you call it 1 9, that's going to be 9 there.
Oh, you mean, but you haven't done the reverse chain roll?
Plus 1.
No, I need to.
Do your reverse chain roll. Wait. Let's see, so you factor that.
D plus 4. U plus 1.
So there, something's fishy. When we pull out the 2, that should be an 18.
Then why is that?
Oh. And that should be a 6, because that 2 is coming out of all three. Yeah, everything. That's coming out of all three. So that's going to put a 9 in the bottom. So you're going to have a U minus 3 over 3 quantity squared. Because we want to write it as a single square. So you could write it like that, then it's a 9. But then we want to write it as a single square before we do the integration.
Oh, yes.
So then you're going to write it as a yeah. Then it's inside the parentheses. How's yours going, Caesar? So
They definitely just put a good friend.
good, so then we're factoring out the 9. Yeah, that's all. Wait, fine.
I've been doing it for.
So this needs a denominator.
That's going to be U minus 3.
You see, right here, as soon as you factor out this 9, there's no 9 here, so it puts 1 in the denominator.
Plus B squared.
And then you're going to rewrite that as U minus 3.
Yeah, I got that one.
What do you mean?
I said you.
You pull it out, it's under the 18.
Squared over 9. 9 into the square.
No.
Square root.
That divided
So
by
just
1.
because it's 27, U minus 3. So,
Zip it along?
I guess it's already in here, so use W.
As you take out the 9, I'm just
James, how's yours going?
So derivative is 1/3. Just bring it over so that 3 dw is just 10u.
Yeah.
So 3 over 18 dw.
Looking good.
Just like 10
All right.
3 over 18. So I have a question.
Yeah.
Unrelated.
Unrelated. Of course. I'd expect nothing less.
318. That's 16. Oh, so we're left with D theta and then the cone goes away. X.
dy for RT. dy this way. That one minus subtract this one. Yeah, because we're using a dy. So it's the right minus the left. So you've got the right minus the left. So if we're finding a horizontal distance, it's right minus left. In contrast to a vertical distance, it's upper minus lower.
So you're at 1/6.
You're just subtracting the right curve.
Wait. I don't want this because I'm doing this.
No, that's okay. That's okay. It's just that when we're going across, we drew our sticking rectangle. On the right side, it's touching this, and on the left side, it's touching that. To find a horizontal distance, we do right minus left. So there's right minus.
I don't know how to. Once you have that,
Yeah.
I think I got it.
All right, let's do it. Let's see if you got it. You tell me what to do.
Okay.
9 plus 9.
I have no clue.
Okay, so everyone agree on the completing the square part?
9 plus 1.
We're going to get u minus 3 squared plus 9.
Yes.
Everyone agree with that?
Yes.
So then we're going to factor out the 9.
Yes.
So we'll get 118. And then here, u minus 3 over 3 quantity squared plus 1.
tangent.
That step, everybody, and now it's in inverse tangent form. You could, if you wanted, if you are into some sort of torture,
Yes.
you could do trigonometric substitution here. But if you don't want to do trigonometric substitution, you can immediately see that it's an arctan. So that's going to be arctan of whatever is in the parentheses. And then the hard part is remembering reverse chain rule. So we look in here, the derivative in here is a third, dividing by a third is multiplying by 3. And then we have that.
No, I
You had an 18.
I didn't simplify.
Yeah. Oh, you didn't. You had a 3 on.
Yeah.
Okay. Okay. Yeah.
Why isn't it
I
minus
think I might
C?
have done something.
It's not minus C because we're conformists. We're sheep. So we put a plus.
We're not.
I see. If you want to put a minus C, if you want to start a new trend in 100 years, all the books will say minus C.
Would my Calc 3 teacher hate me?
Oh, I can't wait. All right, so another integration technique. PFD. PFD, partial fraction decomp. Decomp. Okay, so back in algebra, you've done this a million times where you started with a couple of fractions and you went to the left. You added them. You got a common denominator. You combined them. Right? You've done that a ton where you figure out the greatest common denominator or the least common denominator and you turn it into that. Well, now we're going to go backwards. Why? Because that's so easy to integrate.
But I don't
Right? Both of those are log functions. Those are both in log form, so they're very easy to integrate. So if we can take... So the big difference between this and the last problem is that this denominator is factorable. Right? The last denominator was not factorable, so we had to complete the square. This one is factorable if you know how to factor.
That's the key word.
Keyword. If. So then this is going to integrate really nicely. Natural log absolute x minus 2 plus the natural log times 2 of absolute x plus 4 plus c. So this is going to be why we want to do PFD. If we have a fraction that we can turn into a sum of partial fractions, it'll be a lot easier to integrate. So we're grateful that we have this technique.
Thank you.
Just in case we come across something that's factorable. Ah, perfect. I'll let you read that. So that says nothing. So all this is saying is that if your denominator factors into a bunch of linear factors, let's go back to the previous slide. I'm going to point one thing out. Notice that the factorization of this denominator is what creates each of the partial fractions. Right? The factorization of this polynomial is x minus 2 times x plus 4. Right? That's what this factors into. This factors into x plus 4 times x minus 2. And so it's those factors that create the partial fraction decomposition. So what this crazy looking slide is telling us is nothing more than if the denominator factors, you have a partial fraction for each of the factors that are in the denominator. So that's what that's telling us. So that's it. That's all it's saying. So right down here, here's what it's saying. It's saying, okay, so take this integrand and the partial fraction decomp is going to look like this. We'll have a partial fraction for each factor in the denominator. And the a and the b are constants. And that's what we have to do. We have to go back to college algebra and solve for a and b. So first, we are going to find A and B using the traditional method. Because there are some PFD problems that you have to use the traditional method for. So we're going to use the traditional method for this case where there's actually an easier way to do it. But we want to do the traditional method first just to make sure we understand it.
So would you say that the easier method, would that be valid for every single other question, or is that only those?
It's only valid for linear factors in the denominator. So I'm sure you all remember the fundamental theorem of algebra.
Linear and quadratics.
Every polynomial with real integer coefficients can be factored into linears and quadratics.
Yes.
Right? Fundamental theorem of algebra. Any polynomial can be reduced down. It could be very, very hard to do that factorization. But if you have integer coefficients, you can always factor down to linears and irreducible quadratics. In irreducible quadratic, you need imaginary numbers to factor. X squared plus 1, x squared plus 5, things like that. Irreducible.
But the traditional method will work regardless of any other.
Yeah, the traditional method will work for any of these cases.
It's gonna be like 8 equals A plus B.
So here is the traditional method. So we want to solve for A and B here. So we're going to clear the fraction. So here's the first step, clearing the fraction. So when we clear the fraction, we are going to create our PFD equation. So here is our PFD equation. And now we're back to college algebra. We want to know what are the A and the B that make this true. So what we're going to do is expand everything on the right. And I'm going to rewrite the right-hand side so that it looks a little bit more like a polynomial. So, on the left, we have a polynomial. On the right, we have a polynomial. Two polynomials are equal if and only if the coefficients match. It's the only way. If somebody says that you have 2x plus 5 equals ax plus b, what does A have to be? 2. What does B have to be? 5. So the only way two polynomials can be equal is if the corresponding coefficients match. It's the only way. All right? It's the only way. On the left here, this is a polynomial. What is the coefficient of x here on the left?
0.
0. So this is going to create a system here. We're going to have 0 coefficient of x on the left. Coefficient of x on the right is a plus b. Constant on the left is 8. Constant on the right, 6a minus 2b. So there's the system that represents the solutions we are looking for, A and B. As you know, you can use either substitution or elimination when you are solving a system of equations. Obviously, back from like grade school?
Yeah.
Long ago. And you can divide an equation by a constant if you want. So I divided equation 2 by 2. What do you think we want to do here?
Solve for A or B.
Yeah. So we could use substitution or elimination. Here, elimination makes a lot of sense because if we add these equations together, one of the variables disappears. The b vanishes.
Oh, yeah.
So if we add on the left, we get 4, and if we add on the right, we get 4a plus 0b, so a is 1. So there's our first constant.
So would the other one have to be 7? Because they add to 8 or no?
They add to 0, right? A plus b is 0. So you can plug into this equation. If you plug in 1 right there, you subtract 6, you get 2 equals minus 2b, and you'll get b is negative 1. It's always usually we want to plug into the easiest equation, so that's this one. If A is 1, subtract 1, you get B is negative 1. You can put it into either, though. So you could use substitution if you wanted also. You could have solved this second equation for B and plugged it into the first equation and solved for A. All right, so that is the traditional method. The traditional method, we get our PFD equation and then we equate coefficients. That is the traditional method. Now, let's do the integration. So what this means then, let's call our original integral something. I'll call it an omega. So our original integral is now being broken apart. A was positive 1 into 1 over x minus 2 minus 1 over x plus 6 dx. And that is very easy to integrate. We'll get natural log absolute minus natural log absolute plus c. And that is our final answer. With all of these PFDs, there are a bazillion log properties that you could use. On the exam, it will say you do not need to use log properties to combine. Because you very easily could say, oh, can't we turn this into, and yes, you could turn this into that. But you don't need to do the log properties at the end. Because we're going to get some that are so complicated, and to combine them and use log properties is just too much time.
Where'd you get that for? On the,
4.
yeah, on the.
Oh, over here?
Yeah.
Divide by 2. Divide by 2, divide by 2, divide by 2.
Why do you have them sectioned off like that?
The system?
Yeah.
So here's the system originally, and then I rewrote it by dividing the second equation by 2.
Okay.
How come you divided by 2? 2 get 1?
Because there's a common factor of 2,
Okay.
just to simplify it.
Oh, I see what you do. Okay.
Because those are, if there's a common constant that you can cancel out, it just simplifies it.
Okay, so you're only adding those bottom two?
Yep, this system right here.
Okay.
Yep. So that is the, whoop.
What if we get a linear when we separate and an irreducible quadratic?
We'll get there.
Okay.
We'll get there in the future, not in the present.
Like 10 minutes or?
Yeah,
Okay.
like 30 minutes. Okay, so let's look at, the traditional method is not that hard. We equate the coefficients, get a system, solve for the system. Solve the system for A and B. Let's take a look at the convenient value method. I can't remember, did I put, no I didn't, okay. So let's look at the convenient value method. So this equation right here, this is our PFD equation. So the PFD equation is that. So this is going to be for the convenient value method. This equation is an identity. This equation is true for all x.
Is the 8 always going to be there, or is that just specific to this problem?
Is what going to be there?
The 8.
Well, the 8 is just because that's what was here. So it's whatever the numerator is, it's going to be on the left.
Okay.
So in this case, it was a constant on the left. Sometimes there'll be an x in there. Okay, so that's true for all x. If it's true for all x, it's true for 2 and -6, every single x. So those are the convenient values. The convenient values are the zeros of the denominator factors. So these convenient values, if we plug them in, so I'm plugging in 2, then we get A is 1 and we're done. It's very fast. The convenient value method is very quick. If you plug in -6, we get 8 equals negative 8b. So from that right there, we got to our A and B in just a couple of lines versus that. So the convenient value method is way more efficient if you have linear factors in the denominator.
Are you just, so are the A and the B, like you're kind of just creating coefficients for the two factors? Or like
Yep, so the A and the B are going to be coefficients. When we clear out the fraction, they become coefficients of the two factors. And we're going to say that this equation is true no matter what. So if we plug in a 2, this goes away. Plug in 2 here, we get 8a. When we plug in the negative 6, this one goes away. And that's how the convenient value method works. There's a bunch of cancellations that become 0. So it's really fast. All right, so let's try this one. So first off, in order to use PFD, the denominator must be factored. So let's factor the denominator. You get that. Factor out the x, and you have x squared minus 1. X squared minus 1 factors into x minus 1 and x plus 1. Okay, so the PFD part, 4x minus 2. So now this numerator is not just a constant. We have an x in it. The nice thing about PFD is it's so procedural. It's like mind-numbingly procedural, which is a good thing after doing trig sub. Okay, so this is going to be a over x plus b over x minus 1 plus c over x plus 1. So we have 3 linear factors in the denominator, which mean we're going to have 3 partial fractions, 1 for each factor in the denominator. Any questions? Now let's create our PFD equation. Multiply both sides by the left denominator. So when you multiply both sides by that denominator, you get a whole bunch of cancellation. And that's our PFD equation. So this denominator is being multiplied by each of these 3 fractions. And you get a cancellation of 1 factor with each fraction. Everyone okay with that? So we're multiplying both sides by the left denominator, canceling. Now you can start to see that the traditional method is going to start getting a little more complicated, because here we're going to have to FOIL this out, multiply that out, collect all the like terms. Let's go with the convenient value method. If we just have linear factors, the convenient value method is way easier. So what are the convenient values?
0, 1, negative 1.
Perfect. So the zeros of the factors, those are the so-called convenient values. And then we just plug them in across the board. Plug in 0 here, we get negative 2 on the left. Plug in 0 on the right. Notice that this is going to be gone and this is going to be gone. When you plug in 0, those are gone. Here, plug in 0, we get negative a. So a is 2. Plug in 1 across the board. So 1 on the left gives a 4 minus 2. 1 on the right, gone. Gone. The only one that's not gone is this one when we plug in 1. So we're going to get 2b. plug in -1. On the left, we get -6. On the right, plugging in -1, gone, gone, -1 in there and there. So -2 times -1 is +2. So we get 2c. All right, any confusion? Yeah,
I have a question.
sure,
Can you scroll up?
sure.
It's about like how you match the A, B, and C. Like let's say you put the x plus 1 with the A and then the x.
Doesn't matter.
Doesn't matter. Okay.
Yeah, you'll get a slightly different equation, but you'll end up with the same. In the very end, you'll be integrating the exact same fractions. So yeah, if you put the A over this and the C over that, yeah, it won't matter. Yeah. So now we're ready to write our new integral. So again, it's convenient to call the integral something. So call it I, call it delta, call it whatever you want. So we're going to see omega is 2 over x. And then I think I did x plus, oh, I did x minus 1x. Okay, so plus 1 over x minus 1 minus 3 over x plus 1. So now it looks way easier, because it is. We can integrate term by term super easily. So this will be 2 natural log absolute value of x plus natural log of x minus 1 minus 3 times natural log absolute x plus 1 plus c. And you can see there's a lot of log properties. You could start combining things, but no bother. We'll stop there. It gets to be too tedious. Question?
Will you scroll up real quick?
Yeah, sure.
Can you explain how we know what to multiply with, like A and B?
Right here,
Yeah.
we multiply both sides by this denominator. So when this denominator multiplies to this fraction, that x and that x cancel, leaving us with those two. When this multiplies to the middle one, x minus 1 and the x minus 1 cancel, so we're left with the x and the x plus 1. When we take that and we multiply it by the third fraction, the x plus 1's cancel, so we're left with the x and the x minus 1. You see it?
That makes sense.
Yeah, so we're distributing that denominator, we're multiplying it by each and every term.
Is the convenient value method only specific to if it's x minus 1, x plus 1 versus like x minus 1, x minus whatever? Like if it's both an addition and a subtraction in the factors?
The only condition for the convenient value method is that each of these factors is linear. The power in the x is 1.
Okay.
So the place where convenient could be, if we have something like an irreducible quadratic, which we'll see in a minute, if we have something like x squared plus 4, there's no convenient value. There's nothing that would make an x squared plus 4 0, no integers.
Okay, so if it was x plus 4, x plus 2, and those were the two factors, you could still use this?
Yes.
Okay.
Yeah, so as long as those factors are linear, as long as there's no x squared in there, convenient value method is the way to go. All right, should we take a break? 10-minute break?
Sure.
10-minute break. Welcome. Glad you made it. So what this next slide is showing is that if you have a repeated root, and that's what this square says here, right? That means a repeated root. You have x plus 2 repeated. If the power is not 1, you have a repeated root. And so if you have a repeated root, what this is telling us is that you need a partial fraction for every power of that repeated root. That's what that says.
I'm sorry, I didn't catch that. What shows that it's a repeated root?
A what?
What shows that it's a repeated root?
The power being not 1.
Okay.
So if the power is bigger than 1, it means you've got a repeated root. You've got that root more than one time. Back in college algebra, we called it multiplicity.
Yeah.
The 0 of multiplicity 2, or negative 2. Oh no, multiplicity was positive.
Yes.
Okay, so here's what we're going to do. We're going to take our inside, and when we do our PFD, we are going to have a partial fraction for each power of the repeated root. So that's our PF, our partial fraction for x minus 6. And then for x plus 2, and then for x plus 2 squared. So a partial fraction for each power of the repeated root.
So if it was 4, it'd be another one, x plus 3, and then x plus, or x plus 2 to the third.
Yes.
And then, yeah.
Yeah. So if it was x plus 2 to the 4th, we'd have 2 more fractions. One for the third power, one for the fourth power. You have got it. Okay. Now we clear the fractions. We multiply both sides by the left denominator. We want to clear the fractions. So multiplying by the left denominator, so this whole denominator right here, that whole thing, gets multiplied to this, this, and this. When that yellow gets multiplied by the first one, the x minus 6's cancel, and we are left with a multiplied by x plus 2 squared. When the yellow multiplies to the second, we are left with b, x minus 6, and 1, x plus 2. When the yellow multiplies to the third fraction, the x plus 2 squareds cancel, and we're left with c times x minus 6. So that is our PFD equation. Let's go ahead and use some some convenient values. Now there's only 2 convenient values here. So this is going to create a little bit of a snag. What are the 2 that we see for sure?
6 and negative 2.
Yeah, 6 and negative 2. But that's not enough. We're going to need another convenient value. And since there's not a convenient value that creates zeros, we'll pick something that's convenient-ish.
1.
And we can pick 1. We can pick any constant we want. Usually you pick a constant that's going to be kind of reduced. Like if you pick 0, this side disappears and all these x's disappear, 0. You can pick negative 1 would make this a positive 1. That would simplify it. You could pick 1. You could pick anything you want. Does not matter. I'm going to pick 0. Does not matter. So now the left side, when we have a negative 2, is going to become 64. Negative 2 squared is 4. 4 by 16, 64. Plugging in negative 2 on the right, these 2 are gone. When you plug in negative 2 into either of those, you get 0. Gone. So the negative 2 only matters over there. We get negative 8c. And that we can solve for c. We see that c is negative 8.
Negative 8.
So where did you pull the 0 from again? Did you just kind of decide to use 0?
It depends on the expression you want to use. I'll say thin air.
Okay.
You can pick any constant you want.
So if I wanted to use 7, just because.
Just because. 7's not a bad one. Because 7 minus 6 is 1.
I was thinking of that.
Yeah. Were you or not?
No.
Because that's a random one to pick out of the blue. Because that would create a 1 here and a 1 here. So that's a great one to pick. On the right side. The left side would be a little more complicated because you'd have 7 squared times 16. But that's not a bad one.
Isn't that super positive?
Right here? Let's see. So on the left, we get positive 64. On the right, we get negative 8c, so we divide both sides by negative 8. 64 divided by negative 8 is negative 8. So c will be negative 8. Plug in x equals 6. We're going to have 36 times 16 on the left. On the right, 6 is going to make that one 0 and that one 0. And when we plug it in here, we're going to get 8 squared, which is 64, times a. Well, we know how to divide 16 goes into 16 once, goes into 64 4 times. Divide by 4, and we get that a is equal to 9. Let's plug in 0. 0 on the left gives 0. 0 on the right. All right, let's see. 0 on the right, that's going to be 4a. 0 here looks like negative 12b. Plug in 0 there, we get negative 6c. So what do you think we do now?
Factor out of 2.
We'll divide out of 2. That's a totally good thing to do. So if we divide out 2, that just simplifies this equation. And then what?
Do we take our A and C that we just found and plug in?
Perfect. Take the A and the C that we just found, plug them in here and here, and we'll get the B. Exactly. So we know that 6b, I'm going to add the 6b to the left, will be 2 times A, which is 18, minus, let's see, minus 3 times negative 8 is plus 24. So then we divide both sides by 6. We'll get 3 plus 4, so we'll get 7. That'll be our third coefficient. All right, any issues solving that system? Yeah?
This only worked because this was only like the
Linear?
function. Yeah, linear.
Linear.
Functions. Parentheses.
If we had irreducible quadratics, then we would want to use the other method. Yep. So we are ready to rumble. So we'll rewrite that integral. We found that a was 9. So we're going to have the integral of 9 over x minus 6. And then b, we said was 7. So plus 7 over x plus 2. C is negative 8. So negative 8 over x plus 2 squared. And those are pretty easy to integrate.
So how do you know that this, like, how do you decide which variables are C, A, and B? Like, why?
It doesn't matter.
Okay, so we just went out of order down here in the convenient value.
Yeah, you could. So you can put the a over the x plus 2 and the b over the x plus 2 squared, the c over the x minus 6. Is that what you mean?
Not quite. So I'm looking at the light blue part.
Yep.
And we have 64 equals negative 8c.
So that's found by plugging in this negative 2 right here for all these x's.
For all of the x's.
All the x's. And when negative 2 gets plugged in for that x, this becomes 0. When it gets plugged in for that x, this becomes 0. When it becomes, over here, it becomes negative 8 times c.
Okay. And then, so that's like whatever variable is left over is kind of the one that we're solving for.
Yeah, exactly. Exactly. All right. So these first two are logs. We have 9 natural log absolute x minus 6 plus 7 natural log of absolute x plus 2. And then what do you think we do What do you think we're going to do with that last integral?
Oh,
Any ideas?
is it tangent?
It's not tangent,
U sub.
not u sub. What can we do with that thing?
Expand.
We can move this up into the numerator, can't we? Make it x plus 2 to the negative 2. Right? Which we do all the time if we have something in the denominator to a power, we pull it up and use the power rule. So these two are going to stay the same. Those two are coming down. We add 1 to the exponent and get negative 1. We divide by the new exponent, which is going to make this positive 8, times x plus 2 to the negative 1 plus c. And that is an answer.
But like kind of what she was going off of, once you get your A, B, and C, can't you just write them like I could make negative 8 over x minus 6 and then write like
Oh, no, 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 no,
you
no.
couldn't do
Oh,
something
yeah,
like
you
that?
can't do that. When you
No.
get C is negative 8, it has to go over this.
So it has to stay constant with what you picked at first. like,
Whatever you
over each.
picked.
Okay.
Yeah,
Okay.
absolutely.
Yeah.
Like if we pick different, if you pick this to be A and this to be C and that to be B,
And then you solved it and it was this.
you would still end up with these same fractions.
matching.
Matching
together.
them,
Okay,
yeah.
I see.
Yeah.
Could you explain how we found C again?
So C is found, how we found C?
Yeah.
So we're plugging in negative 2,
Was it B? I think I could do
B?
Yeah.
The one at the bottom? That one?
Yeah.
Yeah. Okay, so there's only 2 convenient values, negative 2 and 6. And so that's only going to generate 2 equations. We need 3 equations because there's 3 unknowns. You learned in college algebra if you have 3 unknowns, you need 3 equations, 2 equations for 2 unknowns. So we need a 3rd equation. And that 3rd equation is found by plugging in whatever x value you want. So you get to choose. So I chose x equals 0, so then that's the left side, plugging in 0 for all those x's. And that gives this equation right here. And then we go up here and grab the negative 8 for C and plug it in there, the 9 for A, and plug it in right there. Does that make sense? Other questions? All right. Are we ready for an irreducible quadratic?
No.
You guys look so prepared. Okay, so if we have an irreducible quadratic factor, this is what the PF looks like. The partial fraction looks like a linear expression on top of the irreducible quadratic. That's it. So the big difference is that when you have a linear factor in the denominator, you have a constant up top. When you have a quadratic factor, you have a linear up top. So in other words, we want to maintain this concept of a proper fraction. But we want to be as general as possible. If the bottom's a quadratic, it's still a proper fraction if we go all the way up to a linear on top. So that's what we're going to do. So here, we're going to take the inside. Everyone agree that this is an irreducible quadratic? How do you tell if a quadratic is irreducible? Don't try every possible factorization. There is a math way. What is it?
Man.
Was that English?
No.
How do we know if a quadratic is irreducible?
Can't factor.
Can't factor it, yes. But how do you tell if it's not factorable? You can't just claim something's not factorable just because you couldn't find the factors. Come on! Quadratic formula?
Oh, yes.
B squared minus 4AC would have to be?
0? Yes. I don't know.
If you're gonna have imaginary numbers, what's B squared minus 4AC gonna be?
Negative.
Negative. Right? So you can just test. B squared minus 4AC is negative. Right? B squared is 4. Right? 8 times C is 8. 4 minus 8 is negative.
Oh, yeah.
ABC. ABC. They talk about the quadratic formula, AX squared plus B. Oh gosh, is it really Monday? It's only Monday. So we have an irreducible quadratic because B squared minus 4AC is negative. Okay. So that is what our PFD is going to look like. Now we do the same thing that we did before. We multiply both sides by the denominator on the left. So multiply both sides by the left side's denominator. When you multiply by this yellow box, times that fraction, the x cancels. So you're going to end up with A multiplied by x squared plus 2x plus 2. When you multiply the yellow box by this, you're going to end up with bx plus c times x.
Quick question.
Yeah?
Could we factor B, C? No, never mind.
No. You cannot factor bx plus c. So we have to use the traditional value method, or it makes more sense to use the traditional value method when we are dealing with irreducibles. So what we're going to do is multiply everything out on the right-hand side. So multiply out that entire right-hand side. And then build our system. Build the system. Build it. What is the coefficient of x squared on the left?
1.
What is the coefficient of x squared on the right?
A.
A.
No.
1.
No.
2.
No. If we look at all the squares, what's the coefficient of x squared on the right?
AB. No.
A plus b. A plus b.
This is hard.
I feel like something's coming out of the vents. I feel like we're being poisoned.
Wouldn't be the first time.
Yeah.
Probably not.
It's rat covered.
All right, so now we look at the coefficients of x. Coefficient of x on the left is 3. Coefficient of x on the right?
A plus and 2A plus C.
2a plus c. All right, there's hope. Constant on the left?
2.
Constant on the right?
2A. A
So
plus
now we know that a is 1. And now we back substitute. If a is 1, go to this equation. C is also 1. Go to this equation. If a is 1, b is 0. So those would be our coefficients. All 3.
Can you go through that all over again?
No.
I forgot.
You forgot what?
Well, it's because I was writing it down and then you
All
got
right,
too
yeah.
far ahead, so
I was, yeah.
So I'm gonna just.
I got confused.
I'm gonna just listen.
Yeah. So you follow up to this step.
Yeah.
So we just multiplied this all out. We expanded that. So in order to build our system, we have to match the corresponding coefficients. So whatever the coefficient in front of x squared is on the left, it has to match the coefficient of x squared on the right. So the coefficient of x squared on the left is 1. And on the right, we have an a and a b. So these are added together, so it's a plus b is the coefficient of x squared on the right. Coefficient of x on the left is 3. On the right, we have 2a plus c. And then constant and constant. Constant is the one that has no x's on the right.
Wait, what? Can you just say that one more time? Sorry.
Wait, which thing should I say again?
I'm just also missing like kind of the coefficient thing and like just the things in the blue.
Yeah. What's the number in front of x squared on the left?
1.
What are the, so the a, b, and c are representing numbers. So what are the numbers in front of x squared on the right?
So A and B.
And they're being added together, right? It's ax squared plus bx squared, which is a plus b x squared.
So you're basically just matching, because we have x squared, we're matching which coefficients are the same on the right side, and they're just variables. So that's why for 3x on the left side, that's, we just have like a single, like x to the power of 1. That's why it's 2ax c. Okay.
Yep.
That makes sense.
Yep, good.
Where'd you get bx plus c?
B, this right up here?
Yeah.
So when we have an irreducible quadratic, we put a linear expression on top instead of a constant expression. So when we multiply this yellow box over here, that cancels with that, and we're left with x times bx plus c. See it?
So on the, so you got 1 equals a plus b. I understand that part. But my question is, when you put b equals 0, how come you couldn't have solve for a instead of b?
Well, we solved for a first. Down here, we got that a is 1.
Okay.
So if a is 1, and we plug that 1 in up here, 1 minus 1 is 0. Right, so this is the one. We can't solve this one yet because we have 2 unknowns.
Oh, okay.
So this one we can solve for a because we only have 1 unknown, so a is 1. And then we plug that 1 in right there, subtract 1, and we get b at 0.
Okay, that makes sense.
So will the numerator always be bx plus c, or?
Yes,
Okay.
unless there's more than 1, and then you could have a bx plus c, and a dx plus e, and an fx plus g, and an hx plus I, whatever the next letter in the alphabet is.
I'm taking English class for 2 years.
I know, it's been a while. All right, so now we're ready to rewrite our original integral. And it's going to be, let's see, a over x, so 1 over x. And then b is 0, so it's 0 plus 1. So we're going to have plus 1 over x squared plus 2x plus 2 dx. So that is going to be our new, let's move this down. We're going to need more space, man. Shocker. Let's move it down here. And we'll call this thing omega. So let's move that. Okay, so that's where we're at. So we plugged in our a, b, and c, and that's the integral that we're looking at. What's the integral of 1 over x?
Natural log of x.
Oh, wow. All of a sudden there's speed in this room. All right. What do we do with that second integral? Is that denominator factorable?
We could try.
We already said it's not factorable. Remember b squared minus 4ac?
Oh.
Right?
Yeah, I remember this one.
Yeah, exactly. You're with me. So when we have a polynomial that's not factorable, what was the technique that we used? Vodka? Is that what you said? What did you say?
Quadratic. She meant to say quadratic. I think it came out as vodka.
Oh, no. Complete.
Complete the square.
Complete the square?
Oh.
Killing me, Smalls. Complete the square.
You complete the
afternoon
square.
class struggle
I
this
am.
morning?
I did.
Did your afternoon class struggle this morning?
This is the afternoon
my
class,
gosh.
clown.
Yeah.
That's the afternoon class.
This isn't a night class.
It's like, what? Oh, God. This is the afternoon class. Right, see the clock right there?
The afternoon class does struggle this much.
Okay, so then we complete the square. Okay. And, oh my gosh, now I'm gonna start making equal signs everywhere. All right, so when we complete the square, we're gonna end up with dx divided by x plus 1 squared plus 1. And what form is that in? Tangent inverse. Tangent inverse. It's an inverted tangent. There it is. And there's no reverse chain rule. All right, but what if there was? What if there was a 3 right there? What would we have to do? The derivative there is 3, so we'd have to do that. If there was a coefficient, yeah. All right. So because it went so well with that irreducible quadratic, let's do 2 irreducible quadratics.
Oh yeah, that's not good.
Anything worth doing is worth overdoing. Let's see it. Thank you. All right, so we're going to rewrite this. Well, first of all, let me ask you. I'm afraid to hear the answer, but do we think that those quadratics are irreducible?
No. First one is imaginary.
Can you factor those quadratics?
No.
No. Those are irreducible. Cannot factor a sum of squares. You cannot factor a sum of squares with. You cannot factor a sum of squares. So this is going to be ay plus b linear over quadratic plus cy plus d over y squared plus 2. So we have 2 irreducible quadratics. We need a linear expression in the numerator for each. So multiply both sides by the denominator on the left. And on the right, you should end up with that first and this second. Make sense? Everybody sees how to do the algebra there? Cancel. It's like cross multiplying. It's advanced cross multiplying. Okay, so irreducible quadratics, we need to go traditional method, so now we have to expand. That means you have to FOIL. Here we go, FOIL. So when we FOIL, it doesn't really matter what direction you do it in. I tend to do it with descending powers, but it doesn't matter. Whatever way works for you, just do it. Whatever works. So that's our foiling. Now we get to build a system. Get to use our hands. Build a system. What is the coefficient of y cubed on the left?
A plus C.
Other left?
Zero.
0. So 0 y cubed on the left, right? You can, if you need to, you can put placeholders in here, right? There's 0 y cubed plus 0 times 0 y squared plus 0 y. So if you want to put these in, of course you can do that. Okay, coefficient of y cubed on the right.
A plus C.
Oh, yeah. All right. Coefficient of y squared on the left? 0, right?
B plus D.
B plus D. Coefficient of y on the left is 0. Coefficient of y. Let's try to mark these off so we're not gonna. So we've got those ones, and then the y squareds are gone. And then what is left? So y 2a plus c. All right. So the y's are now gone. And then all we're left with is a constant. So the constant on the left is 1. Constant on the right looks like 2b plus d. All right. So now we solve that system. And what we notice is that equation 1 and equation 3, they have the same letters. And equation 2 and equation 4, so we'll pair them off. So let's go. Let's see. When I look at equation 1 and 3, if we do equation 3 minus equation 1, that's going to be 0 minus 0 on the left, 2a minus a, which is a, c minus c is 0. So that's equation 3 minus equation 1.
Could you do equation 1 minus equation 3?
Yep, and then you'd have negative a equals 0. Yep. Still 0. Yeah. You can, for sure. So now we have equation 2 and 4. Let's do 4 minus 2. So equation 4 minus equation 2. So 1 minus 0 is 1 on the left side. 2b minus b is 1b. And d minus d is 0. So that gives us 2 of our coefficients. And if a is 0, what does c have to be? 0. And if b is 1, what does d have to be? Negative 1. All right, now we have them all. So we have all 4. So we'll call this original integral something. All right, so our original integral is going to be the integral of a is 0. So is ay plus b. So it's going to be 1 over y squared plus 1. And then it was cy plus d. So cy, that's 0, plus d, so that's minus 1, divided by our second irreducible quadratic, which was y squared plus 2. Yeah. All right. What's the integral of the first one?
Tangent.
Arctangent, is that what you said? Yep. Arctan of y. All right, how about the second one? It is an arctangent. Let's be clever here. We're going to factor out the 2. It's going to factor out in the denominator. So when that 2 factors out, it puts a 2 under this denominator, into that denominator. But remember that our next step is always to write that as a quantity squared. Who is going to brave the waters and tell us what that square has to be? Y over root 2. Joe.
Equation 3, so this
Beast.
minus
So then our final answer, half, leave a gap for reverse chain rule. Inverse tangent of y divided by square root of 2 plus c. So, what goes in the reverse chain rule slot? Root 2. The derivative of y over root 2 is 1 over root 2. Dividing by 1 over root 2 is the same as multiplying by root 2. Beauty.
Wait, can you say that again?
Sure. So now we're in arctangent form. The derivative of this is 1 over root 2. The derivative of that is 1 over root 2. So dividing by 1 over root 2 is the same as multiplying by root 2. So if you divide by root 2, divide by 1 over root 2, that's the same as multiplying by root 2.
Going back to the blue part, where you subtracted the third and the first problem.
3 minus 1.
Yeah, can I see that? Because I just kind of need to visualize it.
So 0 minus 0 is what?
0, yeah.
2a minus 1a.
That's 1A. Oh, negative 1.
No, that's right.
Oh, you're
What you said is right.
Yeah.
And then c minus c,
It's going to be
0. C minus c. So 0, 2a minus a is a. That's it right there.
So do you have a C value there too then? Like A and
C minus c is 0.
Right.
Can you scroll
So
down like
do we have, is C just gonna be equal to 0 then? Like do
C is going to be equal to 0 because if you solve and you get that a is 0 and you plug a back in here, you're going to have the c is 0. And so similarly for the second one, when you do your subtraction and get b is 1, you can plug the b equals 1 into either of these equations to get d. If you plugged in b equals 1 right here, you'd subtract 2 and you'd get b is negative 1. If you plug in b equals 1 here, you subtract 1, you get d equals negative 1. That makes sense? Logan?
Can you scroll down an inch?
Oh, yeah. Making sense? Back to college algebra. All right, so let us try an application, a cooked up application. It's really just PFD. Okay, so we've got this cool little curve from 0 to 1, and we want to find the area. Are we going to use a vertical or a horizontal element?
Vertical.
Vertical element, an upright rectangle. Here is our upright rectangle at x. Wide awake, that rectangle. So we're going to integrate across from 0 to 1. Upper curve minus lower curve. That's how we find area when we have a dx. Upper curve minus lower curve. The lower curve is just 0. So we are finding the area beneath this curve by integrating that. And we're going to go from 0 to 1. There are standing rectangles all the way across from 0 to 1. The denominator is factored. If the denominator is factored, that's a good clue that PFD's a strategy that will be useful. All right, so let's come over and do our PFD off on the side. So we're going to have the integrand. And we are going to mix and match. We have a linear factor right there. X plus 1 is linear. The power on the x is 1, so it's linear. So that'll give us a divided by x plus 1. X squared plus 1 is irreducible. So that's going to be a bx plus c. All right, you take it from here. Multiply that out and find your a, b, and c. If you have questions, ask Joe. He's got this out. He's like PFD ninja. Let me know if you're having any trouble with this multiplication step. It's a simple algebra step, but if you're not seeing it clearly, it might feel more hard than it is. Cruise on. Are you boiling that out all at once?
Yeah.
So that times a, oh yeah. Now, bx squared dx. Yeah, good.
Basic algebra part. Enough.
That one. Is that 2b? Oh, no, that's a 1. Yeah. Yeah, you're fine. And then that's equal to the numerator. Say again? Really?
Yeah, to the downside.
That doesn't sound right to me either.
Oh, but the math works out so much.
All right. I'm a little surprised, but did you get a equals 0?
Starting out, you know?
Where? One?
Oh, yeah.
Sorry,
Like, you have like an 8 starting out.
Yeah.
Or ax squared.
Did you get it right?
Or 8 times.
Yes,
So
that's
it's
right.
A.
Yeah.
So it's distributed.
Oh, do we like multiply this?
Yeah.
CX per D.
Yeah.
To get rid
Or
of
not CX plus B.
That's, okay, that makes sense.
Yeah, so that the yellow blob multiplies across.
Equals negative 1 and C equals 1.
Because the thing in front of the x squared is negative 1. So on that side, it's negative 1. The other side is a.
Oh, that's all good. And negative 1 equals b.
X.
C plus b.
Oh, that's a
0.
C plus B.
That's all good.
Okay.
Oh, where to go now? So then you have to use substitution. Then you'll have to, so you can solve this one for A, plug it in there, and then these two are C's and D's. Does that make sense? Yeah, so you've got to create two that have the same.
Oh, no, it's because it's, shoot.
Oh, wait. The gray one does not.
What would you go after?
Solve it.
So put A.
Substitution. Didn't you tell you?
No.
Yeah, so if we solve this one for A, and you plug it in up here, then you'll have a BC equation and a BC equation.
Okay.
if you isolate A here, you get A equals negative C.
Okay, yeah.
And then
I'm sorry.
There
we get a 1?
Right.
Yeah, I don't know where to go here. Sorry, over here.
Because this numerator is a
So what do I do?
So your numerator is going to be an x minus x
I guess you
squared.
could set.
Oh, yeah.
So that is a negative 1, and then that's a 1, and then my last term 0. They're my constants.
Do substitution.
0 equals. And then
Yeah.
That sounds like something that might be right. I'm just like,
I don't know how to solve these.
Let me just double check this. It'll be x squared.
I guess B, I guess
So then, say what you just said. Yep, that's a 1, so then that's the x. These are C plus B.
The fact that you have to say that.
No, A plus C is x squared.
So elementary, but I would be
X squared, x squared, x squared. So the x squared on the left is negative 1. And that's going to be 0, because the constant over here is 0. That's right. So this is x, this is x, and this is x.
I kind of figured that A
This is
was
x squared, this is
I don't know
x
how to
squared, and this is x squared. So the coefficient of x is 1 has to be b plus c. Coefficient of x, coefficient of x, coefficient of x. And then the x squared is a plus b on the right. And the x squared on the left. And then c is 0. All right, let's go through this and see what happened. So when we multiply the denominator on the left by the right-hand side, you should end up with that. And then we just have to expand the whole right-hand side. So expanding the right side, we get ax squared plus a. Foil this part out. So this is our polynomial. I'm going to rewrite this so that it's in descending order on the left so I don't get confused. Do that. Because we have to make sure that we match the x squareds and the x squareds and the x's and the x's and the constants and the constants. So let's just notice, these are the x squareds. These are the x's. And then the constants, oh, there should be 2 constants over here, a and c. So let's match the coefficients. X squared on the left is negative 1. X squared on the right is a plus c. Excuse me, a plus b. Coefficient of x on the left is 1. Coefficient of x on the right is b plus c. 0 on the left, on the right, a plus c. So that's our system. So how do we solve this? Substitution. All right, there's no 2 equations that match right now, so we have to use some sort of substitution. So here, or you could use elimination if you want. Doesn't matter. Like right here, if you wanted, you could do equation 2 minus equation 3. Like this will get us there. A lot of people prefer elimination. So if we subtract, 1 minus 0 is 1, b minus a is b minus a, and c minus c is 0. Now we have 2 equations with a's and b's. So now we can combine those 2. So let's take these 2 equations and combine them. And if we add those equations together, so let's add On the left, we have 1 and -1, so when we add, we get 0. If we add b and b, we get 2b. If we add negative a and a, we get 0. So we will get b is equal to 0. And
Why
if,
did you decide to do, sorry,
go ahead.
why did you decide to do 2 minus 3? Like, what indicates?
You could do substitution. I just saw that if I subtract these two, the c's will go away.
Okay.
Because somehow you've got to get, you can either combine these two and get rid of the b so that you have AC and AC. You have to pair two of them off so that you end up with two equations that have the same letters.
Would you be able to do,
A matrix? Sure.
What?
I don't know what that is. Could you like set both the top equation and the bottom equation equally to each other if you
Yes.
distributed the negative?
Yeah, absolutely. Yeah, so if you want to deal with these two equations, you can solve this one for A and plug it in there. You can, set each of these equal to 0 and then set them equal to each other.
Okay.
Yeah.
Is there anything stopping you from doing like 3 minus 2 instead of 2 minus 3?
And it might be better to do that. Who knows? So if B is 0, what is A?
-1.
So we plug in B equals 0 right here, divide by -1, we get that A is -1. And then if A is -1, oh no, we already found B. We need C. If A is -1, then what's C? 1. Yeah. Great. Yeah.
I tried doing it the way she just said, how like I solved for A, so then that would be A equals -C.
Correct.
But then when you plug it in, like, I don't know, like.
Okay,
how did that
so
work?
here, if you say that A is -C, then you plug it into the top equation. So you're going to have -1 equals -C plus B.
Yeah, and then I got stuck.
And then you have 1 equals B plus C. I'm just going to change the order so that they're the same. And what happens if you add those two equations together? 0, 0, 2B. So B is 0.
Wait, where'd you get that second equation?
This equation here,
Yeah.
that's just this one.
Oh, you just
And I
choose
just
another
switched
one.
the-
Oh,
yeah.
I see. That.
So you combine two and then combine two and then match it with the other one that's
I
left.
see. Yeah.
All right, so now we are ready to create our, yeah, I will, one sec. Okay, there, A over X plus 1. So A over X plus 1. Okay, so our integral, we're going to have A over X plus 1. And then we have bx plus c. So b is 0, so c over whatever that irreducible quadratic was, x squared plus 1. And our limits of integration were 0 to 1, I think.
Negative natural log work.
So any questions up to that step? So negative natural log. And then arctan. 0 to 1. Does 0 contribute anything?
No.
No. Arctan of 0 is 0. Natural log of 1 is 0. So the 0 is not contributing. So we can ignore that, essentially. So then we're going to have minus natural log of 2 plus arctangent of 1. Arctan of 1 is
1.
pi over 4. It's the angle on the right side of the unit circle with a tangent value of 1. So that's pi over 4. And that is our area.
Yes.
Better be a positive number. Something's wrong. Is that a positive number? Hopefully. Natural log of 2, how much is natural log of 2? Like 0.8 or? Can't be that much. How much, what's natural log of 2?
0.69.
So 0.7-ish, okay. And pi over 4 is more than 0.09. Yeah, that's a very small area, huh? Oh, I guess that's 0.2 up there, so yeah, should be a little tiny area. All right, any questions on the integration?
Are you going to show us the other thing you're talking about for A plus B?
Not so good. What's the other thing?
Like A equals negative C.
Did you say that again?
For like the blue, it would be like A equals negative C.
This here?
No, yeah, got that.
Yeah, so if we plug in A equals, so if we solve this one for A, and we plug it in back up there, we're going to combine these two equations then. And then we get B equals 0, and we're going to get the same A and C. So it's going to play, it should play out exactly the same. It's just that we get our first value in a different way. So this is substitution. This is elimination. Okay.
Wait, can you scroll down an inch for a second? Thank you. Done.
That was fast.
I just needed the box.
Wait, the box? Or what's in it? Volume!
Joy.
Ah, volume's so much better than area. All right. So volume of this solid, we've got the region bounded by these curves, all 4 of these curves, and it's rotated around the x-axis. I don't know if we're going to have time to finish this one, though. Let's do something slightly different. I said slightly different, not dramatically different.
Why not?
So I want you all to write down. So let's take a look at this integral. And I want you to write down the partial fraction setup. All right, so there is the integrand. So just write it down. Don't multiply it all out. Just write down the form. I just want to make sure you're understanding the form. The form. So write down the form for this.
That seems like a lot.
Just make sure that you're seeing. What are you thinking about that x cubed? So is it a linear or a quadratic factor? Is it linear or quadratic? X cubed is quadratic? Convince me.
Oh, like the yeah, like the part that you wrote out. That's what you're talking about.
So it's a repeated linear. So it's a repeated linear. Yes. X minus 0 cubed, right? So it's a repeated linear. You following that?
So there's 8 total letters?
2, 4. I'm not seeing 8. How many are you all seeing?
6.
6.
I might be off by something.
I'm not seeing 6 either.
No.
7?
I'm seeing 7.
What?
7 letters? Are we all seeing 7 letters? James, you seeing 7 letters? Not yet? All right, let's see it. So first off, this right here is a linear factor that is cubed.
I did it for the other one.
So that is like x minus 0 quantity cubed. So it's a linear factor that's cubed. All right, it's not an irreducible, it's not a quadratic. So that first part is going to give us an a divided by x plus a b divided by x squared plus a c divided by x cubed. We need to have a partial fraction for every power of the repeated factor. Every power of the repeated factor. Yeah,
So how come those don't have the ax plus b?
because that's a linear factor. For a linear factor, we put a constant in the numerator. For a quadratic factor, we put the ax plus b.
Wait, how is that?
So that is
Oh,
x.
because it doesn't have like x to the third plus something?
Yes, so it's that. So this is linear.
Can you say what you just said something about for a quadratic factor? And
For a
linear
quadratic factor, you have to have a line in the top, an ax plus b.
It has to be linear.
But if it's a linear factor, then you just have a constant in the top.
Okay, and then how, I think the part that's hardest for me right now is figuring out how to write the equation with the a plus b plus c, like the first time that we do that.
Yep.
And everything else makes sense, so can you just review that again?
Yeah.
Quick?
So the first thing we have to do is identify our factors. So that we have two factors here. We have this quadratic factor and that linear factor, and both are repeated. That linear factor of x is repeated 3 times, and this quadratic factor is repeated twice. So we have a linear factor repeated 3 times, a quadratic factor repeated twice. So what we're going to set up then, we have to have, for any linear, it's always going to be a constant up top. And for any quadratic, it's going to be a linear up top. So this is going to be dx plus e. But we have to have a fraction for each power. So we have to have one more fraction.
Did you just add the parentheses in between the x cubed to make x linear?
To make, just to emphasize that it's linear. Like it's x cubed. It's you can think of it as x minus 0 cubed if you want to think of the linear factors as x minus a, x minus whatever raised to a power. So it's linear. Do you see that as linear?
Yeah, I just don't know why you're making eye contact with me. Like
I
I don't
don't know.
see that it's linear. I understand.
Oh, good. Everybody else see it's linear? X minus 0 is linear. So x minus 0 is linear raised to a third, so we have to repeat that linear 3 times. And then the quadratic is raised to the 2, so we need two fractions, one for each power. So that's the setup. Obviously, you would never be asked to do one like that. Because how many equations would you need? 7. And then you would need a matrix. A matrix is used to solve linear systems where you have more than like 3 unknowns, 4 unknowns. When you get into linear algebra, you'll get there.
I don't want to. Yeah, what if I don't want to get there? I don't want to get there.
Unless you don't want to get there, I guess. All right, I think class is over. Right? Is it 5:15? Yeah. 5:15.
Can I ask you a quick question?
Of course.
Okay, so on this kind of situation, I'm grateful that you did this part.
So, I mean, these just come from, if this is linear, that's constant, if this is quadratic, that's linear. That's just the so that's just the rule for theorem.
And linear is always going to refer to like plus.
So it could be x plus 0.
So if it's quadratic, or sorry, if we had like a cubic thing down there.
Then we have to factor. So that is just sort of the structure that we're always constant of linear.
So there's always going to be just
Yeah, the power is probably zero. Bust out the skin. And this shouldn't be an equal. And then that, if you get how it's coming over here. Yeah, that's perfect.
Well, this is all my work, so.
Yeah, that's
I
perfect.
understand.
That's good. You can understand your work.
Yeah.
But yeah, now,
I mean, it's the same old.
Oh, yeah. Let's look at this one. Here, let me make sure I hit the record button off.